Okay, so two uniform spheres, mass is given, horizontal surface, A is moving as it says. Then comes B, which is stationary. Coefficient of restitution between the spheres is 0.75, so E, which is separation speed over approach speed, is 0.75. I'll write that down as well. Sep over approach. Find the speed and direction of motion A immediately after the collision. So it's going to go into two directions. I'm going to break it up into that component and that component. So it'll be A, I'm going to call it A and B. And what this one's going to do, because it's stationary to start off with, and the impulse must be along the line of center, there can be no change in momentum in the other direction. Therefore, it can't move up or down, and therefore this one must go straight across at C. And the first thing I can do is immediately I can go parallel, so perpendicular to the line of centers, and that will tell me that the initial momentum there must be the same as the final momentum. And because the mass stays the same, that means the initial velocity there must be the same as the final velocity. Of course, if something had dropped off here, then it'd be a different situation. But what we've got is, so for A, what we're doing, yes, for A, we're going to have this bit here, which will be 12 sine 60. So 12 sine 60 will equal B. And so B equals 10.39 roughly. So that's the first thing I've got in that direction. Now I'm going to go horizontally, and so we're going to get the impulse is going that way, so there'll be an impulse going that way and an impulse going that way, and that's the equal and opposite impulse means although the momentum of this one may change and the momentum of this one may change, but because they cancel each other out, we have conservation of momentum. And so therefore we're going to get, I'll write down cons of momentum, and don't forget it's absolutely essential that direction matters when we go this way. So we're going to get total initial momentum equals total final momentum, and we're going horizontally. Let's put that in like that. So what we got, the initial, let's take, in fact, let's just not have a double header, let's have that's going to be our positive. So what have we got to start off with? Well, we've got 12, it'll be this bit here, 12 cos 60 times by the mass. Let's put down mass times velocity. So we've got 12, or 0.8 times 12 cos 60. And then plus the, oh, that's 0, isn't it? I didn't really put that in there. And that will equal total final momentum. Well, obviously it's the mass times the velocity. So that'll be 2c. And then the way I've got it set up here, I've put A going backwards, so it'll be minus 0.8a. And this says that 4.8 equals 2c minus 0.8a. We'll call that equation 1, because I will need that again, because I've got two unknowns in here. I've got a C and an A. I've worked out what B is, so that's great on the B front, but I need to work out what the A is in particular here. So at the moment I'm going to have to get one other equation, and I've done going in this direction. I've done conservation of momentum, so the only other thing I can be doing now is using the separation speed over approach speed. So let's have a go at doing that. E, which is the separation speed over approach speed, equals 0.75. So how fast are they closing in, or how fast the separation speed is going to be A plus C, because it's how fast they're moving apart and along the impulse along the line of centers. And how fast they're approaching, well, it's approaching this bit here, which is 12 cos 60. So 12 cos 60, and that equals 0.75, and so that will give me that A plus C equals times both sides by 12 cos 60 will be 4.5, and I want to find out what A is, so I don't want to have C, so let's get C equals 4.5 minus A, and then sub into equation 1, so that bit there will become there, and that will give me 4.8 equals 2 lots of that bit, so 4.5 minus a minus the 0.8a. That's great, so I've got a's involved here, so 4.8 equals 9 minus 2a minus 0.8a, so that'll be minus 2.8, that'll be 2.8a equals 4.2, and so a equals 1.5. So marvellous, I can now find the speed and direction. So it's going to go backwards that way 1.5, and it's going to go up in that direction 10.39. So the speed equals the square root of 10.39 squared plus 1.5 squared, and that equals 10.5 meters per second, and the angle is, let's work out that angle there, 10 to the minus 1 of 10.39 over 1.5, which equals 81.8 degrees to line of centers away from B, and that's probably as good a direction. When you've got it labelled on your diagram what our angle is there, and possibly if I put the B on here and labelled that as my theta, it becomes very clear. But the same thing, if we actually are thinking about what we're doing conservation momentum, we're saying for A, so we've gone in that direction, we've gone in that direction and use the other one, then we'll just find our way through. And that's 3 done.